Hello and welcome to the Advanced Software Architecture course. My name is Imed Hammouda. This is a lecture on Architectural Styles Part 3. In this lecture, we will cover client-server, pipes and filters, and Blackboard styles. We will start with client-server. The client-server architectural style describes distributed applications that involve a separate client and server system and a connecting network. The simplest form of client-server system involves a server application that is accessed directly by multiple clients. Historically, client-server architecture indicated a graphical desktop UI application that communicates with a database server containing much of the business logic in the form of stored procedures, or with a dedicated file server. More generally, however, the client-server architectural style describes the relationship between a client and one or more servers, where the client initiates one or more requests, waits for replies, and processes the replies on receipt. The server typically authorizes the user and then carries out the processing required to generate the result. The server may send responses using a range of protocols and data formats to communicate information to the client. The client-server style separates client applications from the services they use. This style simplifies systems by factoring out common services which are reusable. Because servers can be accessed by any number of clients, it is easy to add new clients to a system. Similarly, servers may be replicated to support scalability or availability. Here are the benefits associated with client-server. Higher security. All data is stored on the server, which generally offers a greater control of security than client machines. Centralized data access. Because data is stored only on the server, access and updates to the data are far easier to administer than in other architectural styles. Ease of maintenance. Roles and responsibilities of a computing system are distributed among several servers that are known to each other through a network. This ensures that a client remains anywhere and unaffected by a server repair, upgrade, or relocation. Scalability. It is possible to add new clients and servers to the system. Interoperability. Clients can exchange data among each other indirectly via the server component. On the limitation side, the traditional client-server architectural style has numerous disadvantages, including the tendency for application data and business logic to be closely combined on the server, which can negatively impact system extensibility. Second, the cost of maintaining the server is often too high. Third, the server component represents a single point of failure. System operations highly depend on the availability of such element. Finally, the system may perform poorly if the server gets overloaded. Here is a question for reflection. What are the different client-server processing styles? One can think of two different processing styles. Clients and server may communicate synchronously, where a client seen on the slide as process A makes a request to a server seen on the slide as process B and waits for a reply before continuing to process. In asynchronous communication, however, a client makes a request to a server and continues processing without waiting for the client response. Next style that will be covered is pipes and filters. An application may be required to perform a variety of tasks of varying complexity on the information that it processes. Pipes and filters consist of a chain of processes or other data processing entities arranged so that the output of each element of the chain is the input of the next. They are also known as pipelines, by analogy to a physical pipeline. Pipes and filters style is a very simple yet powerful architecture. that is also very robust. It consists of any number of components or filters that transform or filter data before processing it on via connectors or pipes to other components. The filters are all working at the same time. The architecture is often used as a simple sequence, but it may also be used for very complex structures. The advantages of the style includes improved maintainability, scalability, and reusability by allowing task elements that perform the processing to be deployed and scaled independently. On the limitations side, there are several challenges when using this style. For instance, changing and rearranging the order of the filters might be challenging because the filters have been designed to execute in a particular order. Also, the style can negatively influence system performance, as having large numbers of independent filters can add substantial amounts of computational overhead. Further, the filters have to agree on the lowest common data representation in order to allow data processing, which can be an implementation challenge. Here is a question for reflection. Does pipes and filters support parallel processing? In typical pipes and filter systems, processing input data occurs upon data arrival. Having processed the first batch of input, there is no need for filter 1 to wait for the processing of that batch by subsequent filters in order to handle new input batches. This can be regarded as a form of parallel processing, which may contribute to system performance. Next style that will be covered is Blackboard. The Blackboard style, also known as shared data, is used in software design to coordinate separate software agents or knowledge sources that need to work opportunistically and non-deterministically together to achieve a global system behavior. Being opportunistic refers to the ability of an agent to process data once the preconditions of that agent are met. Being non-deterministic refers to the fact that the order of agent processing is not predefined. On the slide, you see a Sudoku board accessed by 3 different knowledge sources. One to take care of columns, one to take care of rows, and one to take care of individual square blocks. The Blackboard style provides a conceptual framework for the design and implementation of systems that used to integrate large and diverse specialized agents and implement complex non-deterministic control strategies. A traditional Blackboard model defines 2 main elements: Blackboard, which acts as the connector element, is a structured global memory containing objects from the solution space. Knowledge sources, which are highly specialized components. The Blackboard style allows multiple processes to work closer together on separate threads, polling and reacting if needed. The Blackboard style comes with a number of advantages. First of all, it is possible to extend the system with new knowledge sources. Second, the system can be regarded as flexible with regard to the order of processing. No predefined processing order is set between the knowledge sources. Third, the system can be regarded as robust in the sense that it has the ability to cope with errors during execution and cope with erroneous input. Specialized knowledge sources can be used to address such situations. Further, Blackboard systems score high on security as data is held and protected by a single element, which is the Blackboard, and does not travel across other elements. Finally, the system promises high performance since knowledge sources interact with the data opportunistically and do not need to wait for each other. There are, however, several weaknesses associated with the Blackboard style. First of all, Blackboard systems are complex and difficult to implement. Second, the Blackboard element which holds the data represents a single point of failure, which may compromise system availability. Here is a question for reflection. How to orchestrate the work between the different knowledge sources? In many Blackboard systems, a control unit is used to manage system operations. The control unit dynamically decides which knowledge source to activate next based on the Blackboard contents, the knowledge source's preconditions, and some control information such as the history of changes to the information on the Blackboard. This is the end of the Architectural Styles lecture part 3. Thank you for watching.